Hello, and welcome to this week where we are going to be looking at applications of partial derivatives and second order partial derivatives to find extrema, local and global extrema of functions, where eventually we'll be able to put that into context for various applied problems. We're following a very similar path to what we did in Math 111, where once we had our techniques for differentiation, we shifted to using those derivatives to find out the behavior of a function. So we had the first derivative test to figure out where we were increasing or decreasing. We had the second derivative test to find local minima or maxima. And we're now going to do basically the exact same thing with multivariable functions. But just as multivariable functions are more complicated to differentiate, finding extrema for multivariable functions is slightly more complicated as well. We're going to look at three different kinds of optimization problems. And when we're working with optimization, the first and most important part is the classification of what are called critical points. This is a term that was used in Math 111, and we're going to use it now with multivariable functions. We're going to be looking for minima and maxima over closed and bounded regions. We'll define both of those carefully. And then we'll also look at finding maxima and minima under constraints. And we're going to use the technique of Lagrange multipliers in order to do that. So before we get into the nitty gritty, I want to go ahead and review some of the terminology from Math 111 with respect to extrema. So the terms that are important here are the ideas of, first of all, a global or absolute max is going to be the largest output of the function over the entire domain. So I always like to think about these terms. We can think about globally and locally, say tallest mountains or tallest buildings. We know that the tallest mountain globally would be Mount Everest, but if we want to know about the tallest mountain locally here in the lower mainland, well, we have to define what that local region is. And so here, another term is the idea of a local or relative max is going to be the biggest output of the function over some small neighborhood. So we need to choose what the neighborhood is before we can start talking about local extrema. And then global and local minima, same definition, but instead of looking at the biggest output, we're going to be looking at the smallest output. Over here on the right, we have a nice little image from the textbook demonstrating and showing what absolute or local max or min would look like. So here you can see the largest output ends up being an absolute maximum on the entire domain of this function versus in this kind of neighborhood around here, this output would be a local maximum. When we're talking about extrema, one of the most important definitions that we need to look at is this idea of a critical point. And we said that in 111, a number x equal to a was a critical point of a function f of x if we had the derivative at x equal to a either did not exist or the derivative existed and it was equal to 0. So this was our definition of a critical point. When I plug in this value of a into my derivative, it's either 0 or doesn't exist. So we need to now define this for multivariable functions. And the definition is almost the same, except for one small subtlety. The first point, we say that a point, a comma b, is a critical point of a multivariable function f of x, y, if we have that both partial derivatives are 0. So here we have to have that the partial with respect to x and the partial with respect to y are both equal to 0, or we have that at least one of the partials of f with respect to x or f with respect to y does not exist. So we only need one of these to not exist in order for the point AB to be a critical point. Now, here at the bottom, I have in bold something to beware of, and I'll emphasize this again. Not all critical points result in extrema. This is a very common misconception made by a lot of students. We'll see in a few slides some pictures that emphasize this point, that a critical point can be critical. It can have that the derivative is either 0 or does not exist, but it doesn't necessarily result in a extreme value. We can kind of do something with the converse of that statement, saying that, well, if I have a local max or min, what can I say about the partial derivatives? And the following theorem gives us that piece of information. It says that if I know I have a local min or max at a point A comma B, then I'm going to have that my partial derivatives are going to both be 0. And the key here is the statement at the beginning saying that we have to assume to start off with that f of x comma y is differentiable at the point A comma B. So we're assuming that we have a local max or min, and we're assuming that it is differentiable, that is, that those partials exist, then our partials must be 0. And it might help to draw a picture in this case. So we're being told we have a nice smooth surface where I can always draw a tangent plane. So I could have a surface that looks something like this, trying to make it and give it some dimension here. So here's my surface f of x comma y. And I could look at the point here where it's obviously a max at f of a comma b. Because I know that this surface is differentiable, it's nice and smooth, I can go ahead and draw what my tangent plane would look like at this point and height of f of a comma b. And our tangent plane would look something like this. So remember that this is the linearization of f at xy at the point a comma b. And in this image with the tangent plane, remember that the tangent plane is defined by using the partial derivative of f with respect to x and the partial derivative of f with respect to y. And we can draw what each of those look like. So we would have in the x direction, so here could be my f sub x of a comma b. And we would also have in the other direction, I could draw f sub y of a comma b. So here, not an arrow to give it some kind of direction. And we have our other f sub x of a comma b. And in this case, we see, trying to change my color here. Oh my goodness, come on. There we go. Okay. We can see that in this case, with that tangent plane being flat, that our change in y is 0 and our change in x is 0. Both of our f sub x at a comma b and our f sub y at a comma b, both of these are going to have to be equal to 0. And we can also say something about the gradient of f at a comma b. The gradient should be 0. And the question here is, why does that make sense? And we can answer that by saying, well, let's suppose that the gradient is not 0. So if the gradient of f at a comma b is not equal to 0, we can use what we know about the gradient and its max or min values. So we know that in this case, we have that the maximum of the directional derivative of f at a comma b is going to be equal to the magnitude of the gradient at a comma b, which we know is going to have to be a positive number based on our definition of the gradient. And so this is going to mean that our function f should be increasing. If the gradient is positive, it means that our function is increasing. And so this would mean that we can't have that our a comma b is not a max. If we're increasing at this point, we can't have that point is a maximum. We're going to have to go up from there. On the other hand, we know that the min of the directional derivative of f is going to be equal to the negative of the gradient of f at AB, which in the same way should be less than 0. So this would mean that our function f is going to be decreasing, the gradient is going down, and so in the same way we would have that the point a comma b is not a min. But we know from what we started off with that apparently AB is a max or a min, so we would have to have that gradient be 0 at that point. Furthermore, remember that the gradient was, the directional derivative was going to be 0 along level curves, and essentially you can think of the maximum value there as a level curve. In order to determine where we might have a local max or a local min, the first point is finding critical points. So here we're going to start off with this polynomial function in x and y, and we're going to try to find the critical points of this function. So again, here, any local max or min occur when we have that our f sub x equals f sub y equals 0. So we need to set up a system of equations in order to do this. We know that we have that f sub x is going to be equal to, we'll have 2x minus 2, and our f sub y is going to be equal to 2y minus 6. And this is a system that we need to solve. And this isn't all that bad to do. We can go ahead and see that this is going to give me that my x is going to be equal to 1, and my y is going to be equal to 3. So we end up getting that we have a possible local max or min at the point 1, 3. Now, in the second part, I'm going to claim that this point is actually a global minimum. So in order to show that it's a global minimum, we have to do a little bit more work. And to do that, we end up looking at our function f of x comma y equal to x squared plus y squared minus 2x minus 6y plus 14. I should say that finding global extrema is a generally more complicated process, but we're able to show that it is global in this case by using a little bit of algebra. So here we can go ahead and can move the terms in this polynomial around so that we get x squared minus 2x plus y squared minus 6y. And completing the square in both of these cases, we need to add a 1 to our polynomial in x, and we're going to have to add a 9 to our polynomial in y. We have 14 to play around with. Here so far I have 10, so I need to have an extra 4 here at the end of my expression. And this way I can rewrite as x minus 1 all squared plus y minus 3 all squared plus 4. Now we can notice that here I have a term that's all squared, a term that's all squared, and a 4. So this entire expression is going to have to be bigger than or equal to 4. But we can realize that since our value f of 1 comma 3, when we evaluate it, plugging in 1 and 3 for x and y respectively, we'll get 4 here. And so this is going to have to mean, so since f of 1, 3 is equal to 4, we have that this is a global min. The smallest that this function can possibly be is equal to 4. And when we plugged in this value into our function, we got 4. So it is a global min. So we know based on that warning and our work in 111 that not all critical points result in extrema. And I promised a picture to demonstrate that, and I'll go ahead and show it here. So I'm going to have 3 examples where my derivative is 0 at a point x equal to a, but in one of them, I don't have a local max or min. So we could go ahead and draw 3 different axes. So here we go, and I'm just going to copy this to save and make it all nice. So copy it, and then we're going to paste it, and paste another. Nice. So here we could look at a function that looks like this. We could look at a function that looks like this, and we could look at a function that looks like this. Now, in the first case, or in all of these cases, when I look at the point x equal to a, assuming that here this a is going to be the same in all of these pictures, and I'm not super happy with how this one turned out, so I'm going to try to flatten it a little bit more. There we go. In all of these cases, at x equal to a, I have a horizontal tangent line. And so by having a horizontal tangent line, this means that my f prime of a is equal to 0. So I have f prime of a is equal to 0 in every single one of these cases. However, in the first example, my critical point gives me a local min here. So here I have a comma f of a is a min, whereas in the second example, my point a comma f of a is a max, but my a comma f of a in the third example is not a min or a max. And so again, critical points can result in extrema, or they could not result in an extrema, as is the case in this third example. So now we had the second derivative test to distinguish and determine whether a given critical point resulted in a local max or min. And so the second derivative test said, and I have like a little typo here that I kind of want to fix up. So we said that if what am I saying here? If x equal to a is a critical point of f of x, we had 3 cases to go through. The first case was that if the second derivative was bigger than 0, then we knew that we had a local min. If the second derivative was smaller than 0, then we had a local max. If the second derivative was 0, the behavior was inconclusive. We could possibly have that the second derivative being equal to 0, we could still have a local min or max. We would just need to do a little bit of extra work. And so now we want to translate this into multivariable functions. What would a second derivative test look like for those kinds of functions? And here it is, the second derivative test for multivariable functions. We start off with a critical point, just as we started off with a critical point in the first version, the single variable version of the second derivative test. So we start off with that critical point. for which we have that our first derivatives are both going to be equal to 0, our first partial derivatives. And we're going to define a new number d, which is going to be equal to the second order partial fxx times the second order partial fyy minus the second order partial xy all squared. So dealing with this is quite complicated. We don't have the time to work through the proof of it. If you have questions, I encourage you to reach out. But what the second derivative test says is essentially relating what the value of this d is to the value of f sub xx. So if we have that this d value is positive and fxx is also positive, then we have a local min. So positive always gives me a local min. If I have that my d is positive, but my fxx is negative, then our critical point is going to result in a local max. If we get that our d is less than 0, then f of ab is not a local max or a local min. It's a special point that I'll define on the next slide. And similar to our first version of the second derivative test, if we have that d is equal to 0, then the test is inconclusive. So we have these cases for the second derivative test that we'll be using in the following examples. So in this example, we're going to classify the critical points of some of these given functions, which the pictures are over on the right. We can essentially tell what we're going to get in the end, but that's kind of beside the point. So here, in order to classify critical points, we first need to find critical points. And so for this first function, to find the critical points, we need to know what f sub x is and what f sub y is. So taking these partial derivatives, we will get 2x and 2y. We want to know when these are going to be equal to 0. And so this will give us that the point 0, 0 is a critical point. So we have a critical point, and now we need to determine whether or not, using the second derivative test, this point results in a local min or a local max. So here, or neither. In the case here, we need to figure out what fxx is. This will give me 2, and this will also be equal to fyy. Then finding what f sub xy is, this will be the derivative with respect to y of fx. So that will give me 0, right? I have that I'm taking this with respect to y, so I get 0. And now we can evaluate that expression d is going to be equal to, I'll have fxx fyy minus fxy all squared, which is always going to be equal to, technically this expression is defined for a particular value of a comma b, but we have here that our second order partials are always constant, so we can just evaluate it normally. This will give me in total 4, which is bigger than 0. So I have that my d is bigger than 0. And I also have that my fxx is also going to be bigger than 0. So because both of these are bigger than 0, according to my second derivative test, I have both being bigger than 0, so I expect that 0, 0 will be a local min. Here I have a local min of 0, 0, and this is verified looking at the image of this surface here on the right. Give the second one a try on your own. Pause the video and I will have it worked out when you come back, and we'll do the third example together. We should have gotten that 0, 0 was a local maximum, as is evident in the picture. We did the exact same strategy, evaluating the partials with respect to x and y, finding the second order partials of our function g, and then looking at our expression d and the sign of our expression gxx. With our d being positive and gxx being negative, we can return to our second derivative test and see that that value of 0, 0 would result in a local maximum. For the third example with h, we do the exact same strategy. So here we're going to be looking at h sub x, which will be equal to 2x, and h sub y equal to negative 2y, where we can again get that our point 0, 0 is a critical point. We can then evaluate our second order partials. hxx is going to be equal to 2. We have that hyy will be equal to negative 2. And we can evaluate that I currently just want to write f, hxy is going to be equal to 0. Then once we look at our expression for d, evaluating that will be 2 times negative 2 minus 0. So here I get a negative 4. Now, immediately, seeing that I get a negative value for d means that I don't care about what happens with h sub xx. By getting that negative d value here, according to our second derivative test, we know that we do not have a local max or a local min. So in this case, we would have that 0, 0 is not a max or a min. What we call this is that it is a saddle point. So it is a saddle point. And the saddle point is, we can see it here over in the image on the right. So here's our 0, 0 point. Notice that if we look at the traces here in the y direction, we are decreasing, whereas in the x direction, we're going up. And so that point of 0, 0 becomes what we call a saddle point. Here, this kind of looks like a Pringle or a saddle. And we have now 3 examples of finding these critical points using and classifying critical points using the second derivative test. Here's a slightly more complicated example where our second order partial derivatives are not going to be as straightforward. But we do get to follow a similar strategy, evaluating our partials with respect to x and our partials with respect to y. So for our partial with respect to x, we get 3x squared minus 3y. And for our partial with respect to y, we'll get 3y squared minus 3x. And we're trying to solve this when both of these are going to be equal to 0. We can do a little bit of simplification here. So for this, we are going to have that our after dividing both sides by 3, we will have x squared equal to y. And same thing on the bottom, dividing both sides by 3, we will have that y squared will be equal to x. Now, because this is a system of equations, we can do a substitution. And by substituting in y equal to x squared in the bottom equation, we can rewrite the system to be y equal to x squared and x to the power of 4 equal to x. So subbing in x squared for y, we get x squared squared, which will give me that x to the power of 4. And then we can simplify this a little bit further, or at least rewrite it in a slightly different way. we have that y equals x squared and that x times x cubed minus 1 equals 0. In the bottom equation, we can see that this is going to happen when either our x is equal to 0 or our x is equal to 1. And if x is equal to 0, so when x is equal to 0, we have that y is going to be equal to 0. And so we would have that the point 0, comma 0 is a critical point. And similarly, when x is equal to 1, we will have that y is equal to 1, plugging it back into this expression in our system. So this is going to imply that 1, comma 1 is a critical point. So now that I have my two possible critical points, we want to classify these. And we do that by now looking at those second order partial derivatives. We have that our second order partial with respect to x is going to be equal to 6x. Our second order partial with respect to y will be equal to 6y. And our partial fxy will be equal to -3, taking the derivative of this expression with respect to y. And so we can then find that our expression for d of x comma y is going to be equal to 36xy. So we have our fxx times our fyy minus our fxy all squared. So this will be minus a 9. And now we want to evaluate d at our critical points. So we have at our critical point 0, 0, we have that d of 0, 0 is equal to -9, which is less than 0. So this implies that we are going to get a saddle point at 0, 0. We can do the same thing for 1, 1. So again, here we have at the point 1, 1, we have that d of 1, 1 will be 36 minus 9, which is bigger than 0. And since then we have something bigger than 0, we can note that fxx at 1, comma 1 is equal to 6, which is bigger than 0. And because both of those are going to be bigger than 0, this means that we are going to have a local min at the point 1, comma 1. So we've completed this problem, finding the critical points and then classifying them by looking at the expression d and evaluating it at the given critical point. So we now know how to find local extrema. And we determined in that very first example that our given critical point resulted in a global extrema, but generally this is really tricky to do and requires a bit more depth in order to understand how and whether or not a given point is a global extrema. And so you can remember from 111, we had the extreme value theorem said that if a function was continuous on a closed interval, that we knew we would obtain a global max and a global min on that closed interval. So to draw that out, to remind ourselves what was meant by that, if we had any kind of a function, say something like this, and we were evaluating it on an interval, say a to b. So here would be a, maybe I want to move that over somewhere here. Let's say here's from a until b. On this interval, I have, if I close the interval, so I'm looking from a closed to my B closed, I always have a global max and a global min somewhere on the interval. And it's possible that the max or the min occurs at the endpoints, just like they do here. Here I have that this value is my maximum. It happens at one of the endpoints, whereas here I have my minima happening inside of this closed interval. And so we want to extend this idea to multivariable functions. And we can do that with an extreme value theorem for functions of two variables. It says that if we have a continuous function on a closed and bounded region, because remember, in this case, my domains are intervals, whereas in multivariable functions, my domains can be closed regions, then f of xy has an absolute max and an absolute min in the region D. So there are two words here that might be slightly unfamiliar to you, those being bounded and closed. The term bounded we ran into when we talked about sequences in Math 112. But just to draw out what is meant by these terms here, for example, we could have a region that looks like this, or a region that looks like this. Both of these are what we would refer to as closed regions. They're completely closed from the inside. We don't have any holes, essentially. We could also draw an example of what a not closed region would look like. So here I'll draw kind of two similar shapes and then alter them slightly. So here I have the same circle, but I'll go ahead and remove a point. So we could have a removal of a point here, and then maybe we go ahead and remove another point down here. This would be an example of something that is not closed. Similarly, we could have a region that looks something like this. So here I have those closed sides, but then I could have a dotted bit here on the end. And so this would be an example of something that is, or two regions that are not closed. And then finally, the last definition we need to run into is what this term bounded means. And so a bounded region is something that can be bound in another region in a finite closed area. So an example there would be a region that looks like this. Because I can look around it, this would be an example of a bounded region, versus we would have maybe a region that looks like this, where it goes on infinitely. The first example would be bounded, but the second example would be not bounded. And these will come into play, particularly once we start talking about integrals and integrating over regions. So as I mentioned, finding extrema generally for global extrema is a tricky process, but thanks to the extreme value theorem, we at least have a method to get around that. So the problem that we're trying to solve is to find the absolute extrema of a function inside of a closed and bounded set. So if we have a function f of xy and we have a closed and bounded set, then we can follow these three steps to find our global extrema. And the three steps that we're going to follow, first of all, we're going to find critical points that are in the interior of our region D. We do this in the same way that we've done before, but I'll show you on the next slide through an example. Once we do that, we need to find the boundary points of D where f has a local extrema, and we'll evaluate f as those points. Finally, we're going to look at all of the values that we found in the previous two steps, the possible outputs, and the biggest output will be the global maximum, the smallest output will be the global minimum. And so here, the point that is most important is that the absolute extrema are either going to occur at a critical point inside of D or at a boundary point on D. And this will be more clear once we actually put it into practice in an example. In this example, we're going to go ahead and apply those complicated steps on the previous slide in the context of an example. So here we're looking at this polynomial function f of xy in a closed region defined by these three vertices of a triangle. And in order to do this, first thing that will be helpful is to draw out our region. We can plot this region in the xy plane. We have our points of 1, 0. We'll have 1, 4, and then we'll have 5, 0. And connecting these together, we end up with the region that we're looking at being this green triangle that I will fill in. So this is my region D that I'm going to be evaluating my function at. So first things first, we're going to find the critical points inside of the region. To do this, we are going to first find critical points in general. So we have that our f sub x will be equal to finding the partial here. This will be y minus 1. And our partial with respect to y is going to be equal to x plus 2. And solving both of these equal to 0 is going to give me that the point -2, 1 is a critical point of f of x, y. So I found my critical points, and here we can see that, well, this point is actually outside of our region. 2, or -2, 1 is actually this point here. And so because this point is outside of our region, we can go ahead and discard it. So here we have that since 2, 1 is not inside of D, it's not in our neighborhood, we can discard it. And now we can move on to the second step of checking along the boundary, which is a more complicated case for us to work through. To check along the boundary, we first need to figure out what the boundary is. And the boundary is going to consist of the edges of this triangle. So we would have this boundary here, which I've labeled and drawn out in purple. And I'm going to call that region B1. I'm going to switch colors so that all this is going to match up. So I'm going to call this region boundary 1. We can also look at boundary 2, which would be this line here. So I'm going to have my boundary 2. And last but not least, I have this boundary 3 here in orange. So there's my boundary 3 in orange. And we're going to deal with each one of these boundaries individually. Let's go ahead and start off with our boundary 1. So with boundary 1, this is happening when y is equal to 0 on the interval x inside of 1 until 5. And when we plug y equal to 0 back into our function f of xy, we have that f of x, 0 is going to be equal to, we will have 3 minus x. This is a function, we could call it g of x, and we can evaluate the derivative of g. We have that since our g prime of x is equal to -1, which is not equal to 0, we're going to have that this implies that there are no critical points inside of our boundary B1. So what have we done? We've said that, okay, I want to restrict the output of my function to be for when my inputs are of the form x comma 0. X comma 0 being points along this line where my x varies from 1 until 5. When I input 0 into my function, I get 3 minus x. My first derivative is -1, which is never equal to 0. So I don't have a critical point inside of this boundary. And now we can do the same thing for boundary 2 and boundary 3. So for our boundary 2, which I had in blue, just trying to match up the colors here. So boundary 2, we have is when our x is equal to 1. And here we're working on the interval of y being between 0 and 4, right? So here we're restricting our x to be 1 between y equals 4 and 0. And so we can do the same thing. We're looking at f of my x is now restricted to being 1. My y is between 0 and 4, but it's still a variable y. And this is going to be equal to, plugging in 1 wherever we see an x, we'll get 3 plus, so here we'll get 3 plus y minus 1 plus 2y, which will simplify to, we'll get that this is going to be equal to 2 plus 3y. And in the same way, we can think of this as a function g of y. And this g of y, so since our g prime of y is equal to 3, which again is never going to be equal to 0, this means again that we have no critical points inside of our boundary B sub 2. We've done B1, we've done B2. The last one that we have to deal with is our final boundary line of B sub 3. And so here we have something slightly more complicated. We need to look at this line. And the equation of this line we can determine is given by the equation of y equal to -x plus 5. And this is when our x is going to be inside of the interval 1 until 5. We can then evaluate what our f of, we're plugging in values of x, but our y's are now going to be of the form -x plus 5. Substituting x for x and -x plus 5 for y, after a little bit of simplification, I'll leave this to you to verify, we'll get -x squared plus 2x plus 13. And now taking the first derivative, so here we end up calling this, say, h of x. When we take the first derivative, so since we have that h prime of x is going to be equal to -2x plus 2, we have that when x is equal to 1, we have that this is equal to 0. And then we also, for x equal to 1, plugging that back into our equation here, when x equals to 1, we get that our y is going to be equal to, we'll have -1 plus 5, so it is going to be 4. So this is going to be a critical point inside of D. So here, this is a critical point. But notice that 1, 4 is actually one of our endpoints. And so we've actually already accounted for it, and we'll see that on the next slide. So once again, we've looked at inside of our region D where there were no critical points. We then looked at the inside of the boundaries. So here we had there were no critical points inside of B1. There were no critical points inside of B2 in the interior, but we did have a critical point of 1, 4, which eventually we were going to check anyway. So here we have that we need to check the endpoints, just like we needed to check endpoints for the extreme value theorem in a single variable, we're going to check endpoints here as well. So here we can go ahead and see that, well, when we plug in the endpoint of 1, 0, we get 2. When we plug in the endpoint of 1, 4, we get 14. And when we plug in the endpoint of 5, 0, we get -2. So we can go ahead and conclude from this information that we have an absolute max at the point 1, 4. So at 1, 4, and we have an absolute min at the point 5, 0.